My name's Freddie Witherden, and today I'm going to be talking about our experiences with using OpenCL in our open source high-order computational fluid dynamics code, PyFR. So, a little bit of motivation. Computational fluid dynamics, or CFD, as I'm sure many of you are well aware, is the bedrock of several very exciting high-tech industries. And it really is an enabling tool that's used in both the analysis and design of a wide range of devices and vehicles. Within the space of CFD, what we're interested in looking at and simulating are unsteady turbulent flows. So I have some examples here which include rotorcraft, aerofoils at high angle of attack, high and low pressure turbine blades, and birds in flight. And these are all scenarios where the flow is fundamentally unsteady, as in it's changing with time. And this unsteadiness makes these problems relatively challenging to solve computationally. Now, when we do CFD, our objective for the most part is to solve either the compressible or incompressible Navier-Stokes equations, or some variation thereof, in the vicinity of complex geometrical configurations. Complex geometrical configurations being important as we want to be able to solve real-world problems, such as some of those which I showed on the previous slide. And within the field of CFD, there are various approaches we can take with varying levels of fidelity. At the highest level of fidelity, there's something called a direct numerical simulation, or DNS, which is where one resolves all of the turbulence scales in the simulation. Whereas at the other end of the spectrum, there's a simulation methodology called RANS, or Reynolds Averaged Navier-Stokes, where we model all of the turbulence scales. Now, DNS has the advantage of being exceptionally accurate in a predictive sense. However, it's also extremely, almost intractably expensive for any real-world flows. As a point of reference, if you wanted to do a full DNS of a Boeing 747 at takeoff, it would take thousands of years, even if you had an exaflop-capable supercomputer. Whereas on the flip side, RANS is relatively inexpensive. You can do a RANS simulation on your laptop of a Boeing 747 at cruise in a few minutes. And between these two extremes, we have a range of intermediate approaches that aim to resolve some of the turbulence, but not all of the turbulence scales. The idea being that they're more accurate than RANS for problems which are fundamentally unsteady, but without the cost of DNS. These include unsteady RANS, detached eddy simulations, and large eddy simulations, with our interest definitely being towards the DNS and LES field, or space. And so, what this means is our simulations are, generally speaking, quite expensive. We need substantial compute resources in order to do our simulations, and even with access to those resources, it's not uncommon for simulation to take several weeks to complete. Now, part of what we do that's slightly different to how most industrial and commercial CFD is done is our choice of numerical method, specifically our use of so-called high-order numerical methods. The specific numerical method we use is the flux reconstruction, or FR approach of Huynh. This can be viewed as a combination of the more traditional finite volume methods, which is what you would find in a solver such as OpenFOAM, ANSYS Fluent, or StarCCM+, and finite element methods which are generally used in the structural dynamics community. The FR approach is also very closely related to discontinuous Galerkin methods, if that's something you've heard of. To give you a very brief overview of how the numerical scheme comes together, let's consider a smooth function inside of a domain. If we were to try and discretize this function using a finite volume method, what we would do is we would first divide the domain up into some number of cells, and then inside each cell we would represent the average value of the function inside that cell, as indicated here. And this is by and large what most commercial CFD codes do. And then when we've got a partial differential equation governing the evolution of our smooth function, we couple these cells together at their interfaces. So each cell is connected to its immediate neighbor on the left and the right. They exchange some information, and that enables us to update the average value inside each cell and hence take a time step. This is often done with a so-called Riemann solver. Now, in flux reconstruction, what we do is we divide our domain into elements, and inside each element we represent the solution as a polynomial of degree p. And crucially, we allow this polynomial to be discontinuous between element interfaces. In a practical sense, this polynomial itself is represented in nodal form, as in inside each element we represent the solution by some number of points. In this example here, I've chosen 4 points, which define a cubic polynomial, and in fact, with those 4 points, they are sufficient to uniquely specify a cubic polynomial inside each of our elements. And as before, with the finite volume sense, what we do is we couple together our elements, so information is exchanged at the interfaces through Riemann solves. Now, the key advantage of this formulation is that with the same number of degrees of freedom, you can get a substantially better approximation of your function. And this can be seen if you compare this slide to the previous slide where I showed the finite volume method. In both cases, we have the same number of degrees of freedom, but you'll see here that by using those degrees of freedom more effectively, the flux reconstruction approach is able to deliver us higher accuracy. Hence, we have greater resolving power for each degree of freedom, and thus, for the same level of accuracy, we need fewer overall degrees of freedom. Moreover, inside each element, there's a relatively tight coupling between the degrees of freedom. And this is nice as it reduces indirection and hence saves on indirect memory access, and also conserves memory bandwidth, both things which are very important for today's accelerators. To try and extend this a little bit into 2D, here I've got flow over a circular cylinder in 2 dimensions, and so to apply these methods in this setting, what we would do is first create a mesh around our domain. You can see we've got more resolution around the boundary of the cylinder, then quite fine resolution in the wake, and then less resolution in the far field. This is one of the advantages of being able to use these types of schemes, is they allow us to relatively easily handle geometrically complex domains. But of course, at the price that your grid is unstructured, and so you have to pay the price of some level of indirection and interfaces. Looking into a single element, I've picked one here in the far field. What we have inside each element is a, in this case, multivariate polynomial, 2D. Here I've chosen to use 9 points, which is sufficient to define a 2D quadratic polynomial inside this particular element. with the same arrangement holding in all of the elements inside our simulation. So this gives us a very direct extension to both 2D and 3D from the 1D formulation I showed earlier. Now, what's particularly interesting about the flux reconstruction approach is that the majority of operations inside of a time step involve moving information from the interior of an element to its boundaries. And these operations can typically be cast as very large matrix products, where you've got an operator matrix which defines what you want to do inside each element in your simulation, and then another matrix which consists of the elements themselves, with each element being represented by its own column. Now, what makes the flux reconstruction approach fascinating from a high-performance computing sense is that our choice of element types determines if these operators are sparse or dense. To give you an example, inside of a triangle, which is a simplex element, these operator matrices are typically found to be dense, in that when you want to move information from the interior to the surface, each point on the surface depends on each interior point, and thus you end up with a fully dense operator, and thus you're very much in the flop-bound regime. Whereas, in contrast, in a quadrilateral element, which is a so-called tensor product element, what you find is when you want to move information from the interior to the surface, that if you choose your points correctly, the stars can align, and what you can find is each point on the surface will only depend on some relatively small number of points in the interior. The overall result being that these elements are bound not by flops, but by available memory bandwidth, which leads to some fascinating trade-offs when it comes to creating your mesh and determining what elements are most efficient and what hardware is best suited for your problem. Now I'm going to move on to our implementation of the flux reconstruction approach, PyFR. As the name suggests, PyFR is written in Python, which is relatively unusual for a large-scale, high-performance computing code. The way we accomplish this is roughly as follows. The high-level structure of PyFR is arranged so that the Python code is responsible for setting up the problem, so reading in the mesh, handling distributed memory parallelism with MPI, and then invoking calls to lower-level hardware-specific kernels which do the actual work. And so within this framework, all of the actual compute is performed by hardware-specific kernels rather than Python code, which is relatively slow. And this Python code is completely hardware independent. Now, of course, the question then becomes, well, how do you go about generating these hardware-specific kernels? And the approach we've taken in PyFR is to observe that within flux reconstruction, two types of kernel are needed. The first are the matrix multiply kernels that I referenced earlier, that handle data interpolation and movement inside of an element, noting that the operators in this case can be either sparse or dense depending on your problem, and what I'm calling pointwise nonlinear kernels. These are the kernels that very much encode the physics of the problem. They include things such as your flux function, your Riemann solve, and the such like. Now, in the case of matrix multiplication kernels, they, by and large, are relatively simple. As a first pass, you can simply call sgem or dgem, or if you're being a bit fancier, you can call out to a specialist library which is able to exploit the sparsity of the operator if you're running on, say, a tensor product element. For the pointwise nonlinear kernels, PyFR makes use of a bespoke domain-specific language, which is based around the Mako templating engine, and this translates our kernels from a common representation into either OpenMP annotated C code, OpenCL code, or CUDA code. These kernels are generated and compiled at runtime, which enables PyFR to take advantage of any specific parts of the simulation, so using information that's available at runtime to make informed choices about how to do this translation. We then generate these kernels, compile them at runtime, and finally have them called by the Python outer layer. To give you an example of our domain-specific language, on the left here I have a kernel in our PyFR Mako language, which defines the flux function for the Euler equations, which govern an inviscid fluid. And this kernel on the left can be directly translated to CUDA, OpenMP annotated C code, or OpenCL. For simplicity, I'll show what the CUDA translation looks like. So going here, what we can see is that this relatively simple kernel on the left-hand side has translated to something that's a bit obtuse and hard to parse on the right-hand side. And there are a few things I'd like to bring your attention to. The first is that this representation abstracts the data layout. So you can see on the left we're doing 1.0 divided by S0, and that has been expanded on the right-hand side to a somewhat more intricate representation, whereby the user who's writing the kernels is completely unaware of how data is actually arranged and laid out in memory. And this is nice because it gives us the flexibility to change our data structures as and when required without needing to rewrite any of our kernels. Secondly, the templating can be done on runtime parameters. An example here is we're using this variable ndims, which is the number of dimensions in our mesh, so 2 or 3, depending if you're running a 2D or 3D simulation. And this enables us to very much write kernels once and have them work in a wide variety of scenarios. And you can see on the right that in this particular case, ndims has been substituted for 2. And finally, it enables us to use Python to generate code. So on the left here, we have a Python for loop. This for loop is executed in order to generate the code on the right, which again gives us a fair bit of flexibility and allows us some very compact representations of the physics. Now, whereas here I showed the CUDA kernel, it is virtually identical to the OpenCL kernel with maybe 2 or 3 lines worth of changes up in the preamble to get variables such as your grid and block dimensions. Overall, this architecture enables PyFR to be performance portable across a wide range of platforms with complete feature parity. And so if something works for one backend in PyFR, it will work for all of the backends in PyFR, and due to the limitations, deliberate limitations of the domain-specific language, is almost certain to be performant. So the domain-specific language only enables you to express things which it knows it can translate efficiently. Another advantage of this structure, specifically the fact that MPI and distributed memory parallelism is handled at the Python level, is you can easily mix and match backends across MPI ranks. So some of your MPI ranks could be running the OpenCL backend, whereas other MPI ranks could be running the CUDA backend, hence readily enabling heterogeneous computing. So let's talk a little bit more now about the OpenCL backend. The OpenCL backend in PyFR was originally written in 2014 and came after the CUDA and C OpenMP backends. It works by using the PyOpenCL wrappers, which provides a very nice, very well documented interface to OpenCL in a very Pythonic manner. And this is truly a fantastic library that I can't speak highly enough of. And part of this comes because OpenCL fundamentally is a C API, and hence it's very easy to wrap and make available to other languages. In addition, another nice thing about OpenCL is it's very much based around this idea of runtime code generation, that your kernel should at some level take the form of a string which you pass to the OpenCL API, and it then takes care of compiling it. So this model fits very well with what PyFR wants to do. Unlike the CUDA and OpenMP backends, where we very much have to generate code, invoke a compiler, write a file to disk, load a library from disk, and it's a bit of a clutch. Whereas with OpenCL, it's very natural. Now, as I said before, we initially started with an OpenMP backend, which was targeting CPUs, and a CUDA backend, which was targeting NVIDIA GPUs. And our motivation behind the OpenCL backend was to enable us to target both AMD GPUs and the Xeon Phi, which had just been released at the time. And as some of you may remember, the first generation Xeon Phi, although it was kind of x86, it was a bit quirky, to the extent where you couldn't run Python and all of our Python dependencies on the Xeon Phi itself. And even if you could, its serial performance left a lot to be desired. And so there was no easy way to apply our OpenMP backend to the Xeon Phi, and thus our goal was to target it through OpenCL. Of course, since then, things have moved on a little bit, and thankfully the Xeon Phi is no longer with us, but AMD GPUs are still going strong, and they're very much targeted, the primary target rather, of our OpenCL backend. But of course, in addition, should one want to, you can also use our OpenCL backend to target NVIDIA GPUs, and with the right runtime, regular x86 and ARM CPUs. So let's talk a little bit about performance of the OpenCL backend, and specifically, how does it compare to the native backends in PyFR? Well, in bandwidth bound scenarios, so this is when we're running on those tensor product elements I referenced earlier, where our operator matrices tend to be sparse, our experience is the performance of the OpenCL backend is usually very good and typically on a par with what I would call native approaches, especially on NVIDIA GPUs. As an example of this, we can consider the breakdown of a Taylor-Green vortex, which is a very classic benchmark problem for turbulent CFD codes. You effectively start with a relatively simple analytic condition in a box with some large-scale structures, and over time, these structures break down into smaller and smaller structures until viscosity comes along and takes care of them. Looking at the performance of this particular test case at two different polynomial orders, remembering that since PyFR uses this high-order flux reconstruction approach, we can choose what polynomial order we want in each element, and this has some impacts on the overall performance characteristics and scalability of the algorithm. So what we're looking at here is normalized runtime on an NVIDIA V100 GPU, where I've normalized it by the performance of the PyFR running with the CUDA backend. And what we can see actually quite interestingly is that at both P3 and P4, the OpenCL backend is ever so slightly more efficient than the CUDA backend. So this is very good, this is very promising. However, OpenCL does have some limitations. I would say the first and perhaps biggest limitation that we've encountered in our experience is the lack of performance primitives. As many of you in the audience know, getting a substantial fraction of peak flops for a dense gem almost invariably requires hardware-specific assembly code. And you can see this if you take a look at a BLAS library such as OpenBLAS. You'll very quickly see that all of the low-level kernels are A, written in assembly code, and B, are specific to one particular Intel or AMD microarchitecture. Now, typically in the high-performance computing landscape, these routines are therefore usually provided by the vendors themselves in the form of BLAS libraries. However, for OpenCL, the lack of these performance primitives means that it isn't possible to call out to these high-performance vendor libraries. And as such, we have to use generic libraries. In the first iteration of the OpenCL backend, DentBLAS was provided by CLBLAS, but in 2018 we moved to the excellent CLBLAST library, which is a vast improvement in terms of its design and its performance, and I believe was actually presented at IWOCL a couple of years ago. It's an excellent library, and they very much get their performance by employing auto-tuning. And certainly if you take the time to auto-tune these libraries, the performance can be reasonable. However, it unfortunately is not competitive in our experience with MKL on CPUs or NVIDIA cuBLAS on NVIDIA GPUs, where you really struggle, even for some of the larger matrix multiplications, to get past 40 to 50% of peak flops for these matrix multiplications, where the native libraries are sometimes 70, 80, 90% of peak. A second issue we found, and this isn't as much of a problem, but it's still worth pointing out, is there's no MPI interoperability. With CUDA, it's possible to pass device pointers, so GPU memory pointers, directly to MPI routines. And under the right conditions, with the right MPI library at the right level of strong scaling, this can sometimes improve performance by 10-15%, both by avoiding the need for costly host-to-device copies, by allowing the device to directly exchange data with an InfiniBand adapter, or do direct peer-to-peer transfers, which can not only bypass the host, but in certain high-end scenarios can use something like NVLink to directly bypass the PCI Express bus completely. And with MPI interoperability, leveraging these features is relatively trivial. Unfortunately, we have not found a way of getting such functionality with OpenCL. We're always forced to copy memory back to the host asynchronously, and then once it's back on the host, kick off a non-blocking MPI send or receive. A third limitation, I think, is something that we can all relate to at some level, is the quality of the implementations themselves. Over the past couple of years, we have observed PyFR giving incorrect results with the MESA OpenCL implementation on AMD VG GPUs, and the Intel graphics compute runtime on Intel Gen 9 GPUs. Sometimes these failures are catastrophic to the point where your simulation will man almost immediately, but other times they're more subtle, only certain configurations will fail. And typically when we've tried to debug this, it appears that certain kernels are being miscompiled, and this is what's leading to the incorrect results. This is something that hopefully the community will work on, and with better conformance testing can absolutely be addressed. So with those limitations in mind, what does the future hold for us, given the increasingly heterogeneous GPU landscape that we're looking forward to? Well, firstly, our big open ticket is how do we best support upcoming Intel GPUs? As we're a Python application, SYCL or data parallel C++ really is not viable for us. We need a C API that can be wrapped and called from Python rather than a bespoke language such as DP C++. As such, our initial support for the upcoming Intel GPUs will be the same way we support their iGPUs, which is through our OpenCL backend. But with the caveats that this will probably mean we will not be able to get good performance for simulations that involve dense operator matrices and really need a vendor BLAS library. On the AMD side, one of the things we're investigating is adding a HIP backend into PyFR. The motivation being that HIP is almost a call-to-call compatible library with CUDA, and so it shouldn't be too difficult to wrap HIP in the same way that CUDA is wrapped, and then have PyFR generate HIP-compatible kernels. The primary advantages being that we can call out to AMD's vendor-specific BLAS libraries, which we expect to perform better than CL BLAST, and also get some degree of MPI interop. I think OpenMPI and UCX are beginning to get support for AMD's HIP platform, and so this is something we're looking into over the next 3 to 6 months, and we'll report back accordingly with how the performance compares with the various OpenCL implementations that are available for AMD GPUs.